Hi, welcome to this project walkthrough for the Search and Sample Return project, the first project in the Robotics Nanodegree program. This walkthrough is meant to give you everything you need basically to submit the project. I'm going to step through the various pieces that you need to modify and show you how I went about modifying them to get to sort of the basic implementation. I'd encourage you to go beyond the basic implementation and even try the challenge of going and picking up the rock samples. But this is just to make sure that, that there's no ambiguity in what we're going for and what you need to do to pull off the project submission. So first off, I'm going to assume that you've gone through the lesson in the classroom and that you have downloaded the simulator and experimented a little bit, maybe recorded some data, and that you've set up your Python environment with the Python starter kit. And if you haven't done those things, you can go here to the project repository, and there are the links you need for getting the simulator for Linux, Mac, or Windows, and the Python starter kit, and some learnings about Anaconda and Jupyter notebooks. So that's what we'll be working with. And so once you've cloned the repository, then you have your environment set up in your RoboND environment here and in the project repository folder. From that point, you can launch a Jupyter notebook, which I've already done. So I can just go over here and you'll get a browser window that looks like this. You can click on Rover Project Test Notebook, and the notebook comes up. So you'll see you've got markdown cells and then code cells, and you can run any and all of these cells by either clicking on the play button up here or just hitting Shift Enter. So first off, so basically this notebook is all set up to just run. First thing you should do is just go through and run all the cells and just kind of see what they do, and maybe even mess around a little bit just to get a feel for what's going on. Basically what we've done is copied and pasted the functions that were defined in the lesson and the quizzes so that you have them all here for convenience to get started with. So first off, some imports. If you cloned the repo a while ago, you might not have this in your imports. This is just added recently because some people's environment doesn't get set up with this plugin, but if you already have it, it doesn't do anything. So we can just run that, and we'll just step through running the cells. So now we're going to grab a random image from this test data set, which is contains this folder IMG, which is just some test images that I recorded, so that you can have a feel for what the recorded data looks like if you haven't already recorded some data of your own. You can change this path to wherever you have your own data if you want to look at those images. So stepping on through, next we have some calibration data. I just included calibration data, including grid images for doing perspective transform calibration, and images of a couple of rocks, so that you can do some color thresholding analysis and figure out what color these rocks are. That's what you want to do to be able to find them later. So next, just stepping through defining the functions that we define in the lesson. So perspective transform does this, where grid cells now appear square on the ground, and that's a good thing. It means we're in a top-down view. Next, color thresholding. So this is just the color thresholding function from the lesson, and when you apply that, you'll see the white areas where you've determined as navigable terrain. Next, you've got your coordinate transforms to go from image coordinates to rover coordinates, and eventually to world coordinates. So these are all, again, just the same functions that were defined in the lesson. Also polar coordinates if you want to find the direction of which way the most navigable terrain lives. We can run those and just do a little test and see, okay, so now we have an image, its perspective transformed counterpart, the threshold of that transform, and then the plot of pixels in rover coordinates with an arrow pointing the direction of the angle of the average pixels direction. So all that's just from the lesson. Now this next cell is kind of the first new thing. Here we're importing pandas, which is just a nice library for reading CSV files as well as many other things. And we'll read in now the robotlog.csv file, which is just the log of things like position and yaw and steering angle and all that. So our delimiter is set to semicolon and decimals set to period. If you happen to be in Europe or somewhere else that uses a comma for decimal points, when you go and record your own data, you probably need to change this to a comma. So just keep that in mind. Sending that the list of images, which is the first column in the CSV file, to a list. And then we're reading in the map of the world. So this is now in the calibration images folder. You've got this file called map.bw. This is the black and white map of the world. So white pixels in this correspond to drivable terrain, and black pixels correspond to everything else. And so for plotting purposes, we'll create a 3-color channel version of that map where the red channel and the blue channel are set to 0, and the map appears in green. We're multiplying the map itself, which is a bunch of 1s and 0s, by 255, so it shows up in the green. And next we'll define this class called data bucket, which is just sort of a convenience thing to put all of the list of images and the X and Y positions in yaw into one convenient place that you can use and refer to when you're inside the next thing you'll define, which is the process image function. So we instantiate a data bucket, call it data, and it's got all of our stuff from the CSV file inside of it. So we'll run that. And now we're going to write a function to process images. So we have all those images in our saved data set, and we want to process them. So we're going to define this function called process image, which will later be fed to one of these MoviePy functions. So what we're doing ultimately here is making a video of our processed image output. So we've got our data bucket, we've got our images, which we feed into MoviePy to give it the source of the data, and then run the process image function on each of those images. So that's what we're going to do. And here the process image function is sort of set up with some boilerplate code to show you what's going on. The to-dos involve basically just doing a bunch of things that we did in the lesson, applying a perspective transform and a color threshold to each image, converting to rover-centric and eventually world coordinates, and then updating the world map. So the world map that we defined within data above, it's up here, self.worldmap, is just an empty array to begin with. And then down here, what we want to do are things like this: data.worldmap of obstacle Y, obstacle X, channel 0, which is red, add some value. Where we find obstacles, we want to add to the world map in the red channel. Where we find rocks, we'll add to the world map in the green channel. And where we find navigable terrain, we'll add to the world map in the blue channel. So this is how we get that nice colorful map coming out the other end, which has got blue and red and mapping out where the drivable terrain is. So this process image function does some processing, and then it gives back this output image. So we can make this output image whatever we want. And in this case, we instantiate it to be just an array of zeros of some arbitrary shape. I've chosen some shape here that I want to work with. And then I can populate different parts of that image with parts of my analysis. So in this case, the upper left-hand corner is just going to contain the image itself, the original image. I'll put the warped image in the upper right-hand corner. And then I'll create this map add image that's a combination using this CV2 add weighted. It's going to add a weighted combination of these two images, data.worldmap and data.ground truth. So basically we're overplotting the world map onto the ground truth, and we're saving that in map add, putting that then into the lower left corner. And we use this NP flip up down, which is what flip UD stands for, to turn the map over. Essentially this is just getting us from image space where the y-axis points downward to world space where we want to view the y-axis as going upward and x to the right. So that's about it, and you can put in some text. This is just an example of how to do that. And MoviePy tends to go one iteration too many. I'm not exactly sure why, but I've just added this line at the end so that you don't error out having too many iterations. Basically, you give back output image each time you run this function, and then MoviePy takes care of stitching all those together into a video. So, all right, let's try this. So, run process image on the data set. Okay, there it's going. I ran on 283 images. And these next cells are just two different versions of an inline video player. So now what you can see is we've made this video where, like I said before, the image in the upper left is the original image, the warped image is over here, and then the map is down here. So now we haven't done any mapping, so it just shows us, if we play this driving around, the warped image over here, and the map down here, there's nothing happening on the map yet. But next, I'll show you the basic steps you need to take to populate this map with navigable terrain and rocks and obstacles. So I've modified a different version of this notebook, which I'll show you here, to include those things. And so let's see, I'll just start from the top and run the cells again like we did before. Nothing changed with all these cells at the top until we get to perspective transform. So if you remember what we did before, let me just show you what the output is here. What we did before is perspective transform this image, and then what we have is the light areas, which we're going to call navigable terrain, and the dark areas, which we're going to call obstacles. But we also have these corners that are just, these are actually just areas that are out of the field of view of the camera. So we don't want to map those necessarily. We want to just map the stuff we can see in the camera. So there's a couple ways to go about this when you want to do map not only of navigable terrain, but also of the obstacles which appear dark. You could first do a color threshold and then do the perspective transform so that you already know which pixels are obstacles and which ones are navigable terrain. Or you can do what I did, which is just to create this mask showing the field of view of the camera in the perspective transformed image. So I did that by adding one line to the perspect transform function, which just takes runs the same transform on an array of ones. So this is an array of ones that's just the same size as the image and only one color channel. And what that gives me back is this map of ones where there's basically valid information where the camera can see and zeros elsewhere. So I'll use that later to identify obstacles. So and this is the modification that I made, add that line and then return mask as well. So like I said, there are other ways to do this, but that's just how I chose to go about it. These other cells here are the same, color thresholding and coordinate transforms. And then I've added this other function called find rocks. And this is just it's just very similar to our color threshold from before, but it's applying this tuple of RGB color information here and saying needs to be greater than the red value, greater than the green value, and less than the blue value. So in analyzing these rock images, I found that rocks tend to be bright in red and green and very dim in blue, or dark in blue. So I can use this particular transform to get, or this particular threshold to get the pixels that I want. So when I run this, I get, from an image like this, I get back just the pixels where the rock is. So that's nice. Now I know how to threshold for rocks. And so we're ready to populate our process image function. So again, here's the data bucket. I'll just run that cell. And then what I've done with process image is just to apply all the functions that we listed above, basically. So you've got perspect transform, which now returns warped and mask. And then threshold that. And now I'm going to create this obstacle map, which is just the threshed map -1 times the mask. So, and the absolute value of that. So basically I'm going to get back ones everywhere the threshold map was 0, and then multiply that by my mask, which has zeros where that's outside the camera field of view. So this basically just gives me the map of where obstacle pixels are. This is again the map of navigable terrain pixels. So we'll then convert to Rover coordinates and then define some things like our world size. This is just the world map shape. The scale, if you remember this variable dst size, is just defines how big of squares we're laying out in the perspective transformed image. You can look at that above. X position and Y position, we're just extracting these from our data bucket, this data.xpos and data.ypos. Same thing with yaw. And then we're ready to use these functions that we defined above, x world and y world. Pixels are now going to be given by pix to world from our thresholded pixels. Now we're going to do the same thing, extract these obstacle x and y pixels in rover coordinates, convert them to world coordinates. And now we want to do this step of updating the world map. So we've got these y world and x world and obstacle y world and obstacle x world. And so world map of the blue channel, we're going to update to be 255 where we found navigable terrain, and in the red channel we'll update where we found obstacles. So now there's going to be some overlap between these two, and we have to decide what we believe more. What you can play around with this and try, for example, just adding 1 each time you find a pixel here, and then deciding, oh, if there's more counts in this pixel for the navigable terrain than there is for obstacle, I'll call it navigable terrain. You'll have some conflict here, but anyway, I'm just doing something very simple here. I'm saying if the blue channel is greater than 0, then set the red channel to 0. So I'm just saying if I found it to be navigable terrain, then I will just assume it is. And we don't want to have that overlapping with the obstacles. So next I'm going to use my find rocks function to make a rock map. This is going to be now just like our thresholded image or the obstacle map, but we're using find rocks to apply that color threshold. And then we ask, okay, did we find any rocks? If so, then we'll go through and convert rock pixels to rover coordinates and to world coordinates, and then update the world map in the, in this case, I'm just, so I can make it a little brighter, I'm updating all channels to 255. You can do this to just the green channel or all 3 channels if you want to see it in white. So then the rest of this is just the same thing. Output images, original image to the upper left, warped image to the upper right, and then this overlay, which will now actually have something in it in the lower left. So there you go, run that, and we'll run the MoviePy video generator on that and see what the output looks like. All right, so in the still, you can see that there's something different about this map down here, and then if I hit play, it takes off, and you can see, okay, so we're mapping blue where we think the navigable terrain is, red for obstacles, and this little blip right here is actually showing where we found a rock. So if I play that again, you'll see it appear as we drive by this rock very quickly. So we saw that go by, and we've now mapped it in the world. So it doesn't look like a very good map yet. What you'll want to do to improve the fidelity of the map, so the fidelity is the accuracy, basically how many of these navigable terrain pixels actually landed on valid map pixels. So if you want to improve that, you got to play around a little bit with how you're thresholding for obstacles and navigable terrain and how you're kind of deciding which is which. But this is already, reasonably good. You're getting better than 50% accuracy of where the map is, and that's a good start. So once you've gotten this far, you're basically ready to take the contents of your process image function and bring those into the perception step function, which is in perception.py. So we'll do that next. All right, so here we are back in the project repository on GitHub, and what we're going to do next is take a look at the code in these Python scripts that come in that are in the code folder. So we've got decision.py, drive rover, perception, and supporting functions. So once you've cloned the repo, these are in your code folder. So that's where I'm at here. Can list those out. All right, they're in there. And bring those up in your favorite editor. And so I'll basically just step through what's in the code that comes in the repo, and then we'll get into how to modify it to make the rover drive autonomously. So the kind of main script is this drive rover.py, and this was also kind of covered in the classroom. This is the script that calls all the other functions from the other scripts. So basically you start with a bunch of imports, and then these imports right here are bringing in the functions that either are predefined for you or you define yourself. These perception and decision step are the ones that you're going to focus on defining yourself. So then some socket.io stuff. We're going to read in the ground truth just like we did before, this map, and make a color map where the ground truth appears in green as well. And then we define our rover state class, which has all of the interesting information that we want to maintain about our rover. I'll just comment on a few of these so that in case there's any ambiguity here. Start and total time are just to keep track of the time. The image will get updated each time, as well as position, yaw, pitch, roll, velocity. All these things come from telemetry. Right on down to nav angles. So then nav angles is something that you'll be providing yourself. So this is something where once you've converted the navigable terrain pixels into polar coordinates, this is the angles of all the pixels, and these are the distances of all the pixels. So you'll see later how those get populated. The ground truth is just that map we created. The mode will start out in forward mode, but this is something you can modify later on as you want to make a more complex sort of state machine for your rover. If you want to have multiple different modes, you can say, okay, now we're going forward. In that case, do something. In the case that you're stopped or in some other mode, then you can have a different set of decisions. This is just going to be the maximum, or rather, this is the throttle setting for when you're wanting to throttle, the brake setting for when you're wanting to brake. These are just some pretty arbitrary values, but basically stop forward and go forward are some number of total navigable terrain pixels in the field of view that will initiate stopping and similarly initiate starting again. So this will make sense a little bit more when we take a closer look at decision step. Basically, these are just saying if you're seeing very few pixels in front of you, less than 50, then stop. And if you see plenty of navigable terrain in front of you, then go ahead. Max velocity is 2 meters per second. You could mess with that if you want to go faster or slower. The vision image is what's going to appear in the lower left, actually just above the rover's camera image itself. So this is the image that you can put whatever you want into, but in the videos in the classroom, I'm putting in the navigable terrain in blue and the obstacles in red, which are in the warped perspective. World map is, again, same thing we had in the notebook, an empty array to start with that you'll populate with the pixels for navigable terrain, rocks, and obstacles. Some of the stuff about samples, you don't need to worry about this if you're not going to go chase after the rock samples, but you can look at how these get used inside of the supporting functions script. And then these are also if you want to pick up rocks. I'm not going to get into that right now, but you can play with those if you like. So we initialize a rover and then define this telemetry function that is basically going to be what we do each iteration as we get a new frame from the camera and a new set of telemetry data. So you don't need to worry much about what's going on in here. You can sort of study it line by line if you like, but the important part is that if you have basically valid telemetry, then we're going to go and execute the perception step and then the decision step. And what this is saying is do a perception step, meaning apply all of the vision techniques that you want to apply to decide what you see in your field of view, and then make a decision about what to do based on those. You'll then, these get created automatically using this create output images function. These are going to be the world map image, or rather I think that's in image 2, and then the vision image in image 1. So a little bit of logic here in case you're actually trying to pick up stuff, but for the most part, if you're just going for navigation, then the commands that you want to send to the rover are the throttle brake and steering and the output images. So then you'll use this send control function, send the commands for throttle brake and steering, and then the images to populate in the on screen. So those are the important parts of Drive Rover. These are just some function definitions below here about sending controls and sending pickup and all this other stuff, but you don't need to modify anything in Drive Rover if you don't want to. If you want to modify rover state to track other things about the state of your rover, you're welcome to do that. So I'll just touch on supporting functions as well before we get into the code that you're going to modify. And so these are just some things like update rover. This is going to take the new telemetry, which is stored in data, and update all the values within our rover object. So velocity, position, yaw, pitch, roll, all that stuff. And then it does some printing. If you want to not have it print every time you iterate, then you can just comment this out. And create output images, as I mentioned before, is just for creating the images that will get into that will get populated on screen. You can mess with this if you want. You can have it put other images up if you like, but it defaults to putting the map in the lower right hand corner and the vision image just above the rover camera image itself. So you can have a look at this, see how it all works, but you don't need to modify anything here. Putting some text out to show how much you've mapped and what time and how many rocks you found and all that stuff. So that's about that. Then the important parts that you need to fuss with are decision and perception. So let's look at perception first. So perception comes pre-populated with all of the functions that were defined in the notebook. And so you're welcome to use all of those and also add or modify these functions, add new functions and modify these functions as you see fit to define, to include in your perception step function. So this is like the process image function in the notebook. This is where you're going to take in in this case, you take in the entire rover object, and then you have access to all the values like the image that the rover is seeing from the camera and the X and Y position of the rover, the yaw, the velocity, steering angle, all these things. So you're going to use those things to the image in particular to do some analysis and decide what the terrain looks like in front of the rover, and then store basically the output from the perception in various fields inside the rover. So like example, rover.vision image you can update with your thresholded binary image for obstacles, and vision image in the green channel, maybe with rocks, and navigable terrain in the blue channel. And then for the map, again, you can update just like we did in the notebook, and use the red channel. So this is actually going to be expected now by the supporting functions that do analysis on how well you're mapping the world. So you got to put the rover.world map navigable terrain in the blue channel, same as we did in the notebook, and that's really the only one that matters. Well, unless you're sorry, the rocks will be counted as well. You have to find at least one rock, and that won't actually show up as a rocks found. It'll just populate on your map. It'll show where you found a rock. So finally, you want to convert these pixel distances, or the rover-centric pixel positions, to polar coordinates. And the reason for this is that the default in the decision step is to use these angles to decide which way to steer. So you can mess with that and you can do different things, but that's just the default. So we're going to go through like the simplest possible implementation, and that involves doing this analysis to update the images, and then updating the nav angles field on the rover. So finally, you've got decision. Decision step is a function inside of decision.py, and this has just been set up with a simple decision tree where you can it basically checks if nav angles is not none. So if you've done anything with nav angles, you've put some data in there, then it's going to try to make a decision based on that. If you don't do anything, then this is what gets executed as the decision. The rover.throttle gets set to whatever the throttle setting is. steering and brake set to 0. So basically, it's a very boring rover if you don't do anything with the nav angles, or if you don't rewrite this to consider some other state of the rover. But we can take a look at what this does now. So everything is ready to go out of the box, and we can just see how it works. So we're in the code folder, and we could run drive rover.py. Comes up saying not recording on this run. That's fine. All right, so we can go ahead and start up the simulator, get our choice of screen resolution and graphics quality, hit play, and now we can go ahead and click on autonomous mode. And because our script over here is running, you can see it's iterating through, getting telemetry, and the rover just drives straight until it runs into something. So it's not a very good autonomous vehicle yet, but by modifying perception and decision step, you can get to the point where the rover will pretty quickly drive on its own and drive somewhat decently to start with, and you can improve on that. So let's just kill this and go on and do that next. So over here, I've got a modified version of these scripts, and in fact, the only thing I've modified is perception.py. So we've got, again, all the functions that were defined in the lesson and in the notebook. And then I've gone ahead and made the same modification to perspect transform as I did before, adding this mask and outputting that. And then I've added the find rocks function, which defined in the notebook as well. And so then within this perception step, I'm going to execute all of the things that I did within process image in the notebook. So I define the perspective transform points, source and destination points here. Go ahead and perform the perspective transform on the image. This has to be rover.image. Just copied and pasted some things, so it's a little messy here. Hopefully it works. So let's see. So then perform the perspective transform on the rover image, rover.img. Then threshold that, make an obstacle map, same way we did in the notebook. And now I'm going to update rover.vision image. So this is just to show sort of what the perspective transformed result looks like. And we're multiplying threshed by 255 and obstacle map by 255. This is because these are just ones and zeros, and if you output them as just ones and zeros, they won't show up. You need to multiply by 255 so you can actually see the colors. Now we'll convert, just like we did in the notebook, to rover coordinates. Define world size and scale again. Convert to world coordinates for both navigable pixels and obstacles. And now we're going to update the world map just like we did in the notebook. In this case though, I'm going to, rather than just set this equal to 255 wherever I find navigable terrain, I'm going to say plus equals 10. And so this is now, every time I update this, I'm just going to keep adding, and then in the supporting functions script where these images get considered in order to make them into a map, we're basically going to scale first these images, scale rover.worldmap and of the blue channel and the red channel. You can take a closer look at this if you want to know exactly what's happening, but we just want to make sure it shows up nice and clean in the output image. And then we're going to do this step right here, which is likely nav is going to be pixels that are likely navigable terrain pixels. And so I'm saying if the navigable terrain values greater than or equal to the obstacle values in that image, then let's just set the obstacle map to 0. So this is in an attempt to produce a clean output image and also have better fidelity of the map on the output. All right, so each time we find a pixel of navigable terrain, we add 10 to the blue channel. Each time we find obstacles, we add 1 to the red channel. So as you can see, I'm favoring anywhere I discover navigable terrain. But if you discover a whole lot of obstacles in one pixel, then you will deem it to be an obstacle. Finally, something we didn't do in the notebook, but which the coordinate or the polar coordinates function exists in the notebook as well for, is this conversion to distance and angle. So you can run that, and then you can update rover.nav angles. Remember, this is what your default decision step function is going to be looking for. So same thing, then you can go and look for rocks. And in this case, I've modified things a little bit so that rather than just adding all of the X and Y positions of rocks, I'm going to take basically the one that's closest to me. And the reason for this is that if you look at the perspective transformed image of the rocks, they get sort of sprayed out along the radial axis just because they're not flat on the ground. They actually have a vertical dimension to them. So anyway, you can kind of dig into this and see exactly what's going on here. After I've converted to radial coordinates, I take the minimum distance rock pixel, call that the center point, and then update the rover world map to be 255 at that center point. And then I'll also put those rock pixels into the world map, into the vision image rather. Okay, so that might sound like a lot, but basically this is not doing much at all different from what we already covered in the notebook, and it's essentially just applying all the functions that you already have. So you gotta do a few tricks here and there to get things to come out right, but basically that's all you need to do. So just populating this function should be enough to well, since we've added this nav angles, now when we call the decision step function, this case will be true, and we'll step through this decision tree. So basically I'll tell you a little bit about what's going on here. This is just kind of a bare bones basic decision tree. You can modify this, you can throw it out and start from scratch, but we're just saying if we're in forward mode, okay, then if we have more navigable terrain pixels in front of us than the stop forward value, then we'll go ahead and either adjust, we'll throttle if we're less than max velocity, or we'll just coast if we're actually going the max velocity. And then we will decide on a steering angle based on the mean angle of the nav angles. So the steering angle's got to be clipped between -15 and 15. Those are the maximum or minimum and maximum values you can use. So simple stuff, just deciding which way to go, whether or not to throttle or brake. If in fact there's not much navigable terrain in front, then we'll say throttle equals 0, step on the brakes, rover mode equals stop. And then the other case would be if we come into this function in stop mode, then we try to figure out whether or not we can go again with the rest of this logic. So I'll let you explore that a little bit, but basically this is something that, as you'll see in a moment, allows the rover to drive somewhat decently, but you'll want to modify this to make it work better. So let's see, if we open up, let's first of all go over here, and now we're in the edited code folder, and we can run drive rover over here. So this is a new drive rover, well basically same drive rover but a new perception function, and we'll see how it drives. So we've got the server up, and we can open up the simulator, hit autonomous mode. Okay, so the rover is driving. You can see the map getting populated down here. You can see over here the vision image, which is the showing for each frame of the camera, for each frame of telemetry, what the navigable terrain versus obstacle pixels look like. And so as we step through each frame, then the map gets updated down here in the lower right. And you can see the logic is doing a reasonable job of driving the rover back down into this dead end. And then you can see as we get close to the dead end, this navigable terrain, total navigable terrain shrinks down to almost nothing, and we hit the stop mode, turn around, decide, okay, now we can go forward again. And off we go back down the narrow alleyway here. And so this map is not looking great yet, but it's doing a reasonable job. The fidelity is at 75%, meaning that we've basically got 75% of the blue pixels that we've plotted on this map are corresponding to underlying ground truth map. And that's good enough for this project. You won't see any rocks found until you actually go and pick them up, which is part of the challenge. So what you will see, however, is as we drove by this rock, you can see it got populated on the map down here. So this white square is showing that you found a rock. So in terms of passing the project, you just need to find one rock. And so now we've already found one rock. There's 6 of them scattered throughout the scene each time you start the simulator. But for the basic passing submission, you just need to find one rock. So we're now over 50% mapped. Fidelity is getting a little worse, but it's not horrible. And the rover's doing pretty good. What you'll find is that when you launch this, depending on the start configuration of the rover, it may get into sort of a confusing situation where it just goes in circles in some corner, or it gets stuck behind a rock, or it does something else. You can play around with this by taking over. And so if you see there in the top, when I hit the arrow keys, it shows up in manual mode up here. So I'm driving now. I'm in autonomous mode. We're still mapping, but I'm able to take over. So if you get stuck, you can keep playing with it by taking over, and then just let the arrow keys go, and you'll be back in autonomous mode. So that's basically it. So modifying the notebook in the way that we walked through, and then essentially taking those functions and definitions and bringing them right into the perception step should get you up and running with this project to the point where you can, if you just don't want to do anything else, you could submit it as is. This is now, we've mapped over 70%, fidelity's still above 50%, and we found one of the rocks. So, right, so that's it, and good luck with taking this project to the next level and even solving the challenge if you decide to do that.